Hello, my dear students. Welcome to another opportunity to enrich our knowledge in basic calculus. Today, we shall discuss the limits of transcendental functions. Do you know why they are called as such?
Transcendental functions are functions that cannot be expressed using a finite combination of algebraic operations of addition, subtraction, multiplication, division, raising to a power, or extracting a root. Examples include the functions logarithm of x, sine x, cosine x, e raised to the x power, and any functions containing them. Such functions are expressible in algebraic terms only as infinite series. In general, the term transcendental means non-algebraic.
There are many real-life examples of transcendental functions.
One of those is the situation illustrated in the problem. When the lockdown was implemented, a family has received 20 kilos of rice as relief. In order that it will last for some days, the mother thought of strategy. Every day, she will just use 1/10 of the rice that they have received. Just in case the cooked rice will not suffice to feed everyone, she will just mix it with corn or sweet potato. Will there be a time when they will have no rice to cook? To know the answer to the question, we can make a table of values or we can determine the function that can model the given situation and then analyze the graph to arrive at a conclusion. To start, we identify the variables in the problem. The variables described in the situation are the day and kilos of rice left per day. To get the kilos of rice left for each day, we will multiply 9/10 by the number of kilos left prior to the given day, since for each day, 1/10 of what is left is consumed. For day 0, there will be 20 kilos. To get the number of kilos of rice left for day 1, we get the product of 9/10 by 20, giving us 18. To get the number of kilos left for day 2, multiply 9/10 by 18, giving us a product of 16 and 2/10. We do the same for the succeeding days. As we compute for the number of kilos of rice left in day 200, the value is very small. It is nearly zero. Yet, we cannot say that there is none. With the given data and exploring more about the given conditions, we can say that the family will never run out of rice. In general mathematics, you have learned how to illustrate this kind of situation through exponential functions. We can say that it is of the form y equals a b raised to x, where a is a constant, b as the rate of change, and x as the independent variable. With this, we can have our working equation as y equals 20 times 9 over 10 raised to x. Since we are asked to find out if there will be a time that the family has no more rice, it implies that the time is indefinite. Applying the concept of limits of function, we will have to evaluate the limit of 20 times 9 over 10 raised to x as x approaches positive infinity. Graphing the function, we will have a curve which has a decreasing trend. In the graph, we can clearly see that as x approaches positive infinity, the value of the function approaches 0. Hence, the limit of 20 times 9 over 10 raised to x as x approaches positive infinity is 0. It is consistent with our conclusion that they will not run out of rice, but in the strict essence, the amount of rice will be extremely small that it can be considered insignificant. Now let us explore further the limits of exponential functions. In general mathematics, you have learned that an exponential function is a relation of the form y equals b raised to x, where the exponent x is a real number and that the base b is a positive number not equal to 1. Just like any polynomial function, the limit of exponential functions can be evaluated using table of values or graphs, or by merely substituting the value at which x approaches 2 whenever applicable. Consider example number 1. Find the limit of 3 raised to x as x approaches 2. Let's have first table of values and then verify our answer using the limit laws and the graph of the function later. Remember that you can use your preferred values for x as long as you use values which are getting closer to the given value of a. In this case, we have a equals 2. The limit has two sides. We evaluate first the left side limit by substituting to x values at the left of 2. We can see that as x approaches 2 from the left, the value of f of x gets closer to 9. Hence, the limit of 3 raised to x as x approaches 2 from the left is 9. We also do the same in evaluating the right side limits. However, at this time, we consider the values at the right of 2. Now looking at the values of f of x, as x approaches 2 from the right, we can say that the value gets closer to 9. Hence, we have the limit of 3 raised to x as x approaches 2 from the right is equal to 9. Since both the left and the right side limits approach to 9, we therefore conclude that the limit of 3 raised to x as x approaches 2 is 9. Let's verify by applying the limit laws by substituting 2 to x. Evaluating the function at x equals 2, we will have 3 squared, which when simplified will give us 9. Consequently, the graph shows that x approaches 2. The function gets closer and closer to 9. Let's take a look at example number 2. Find the limit of 5 raised to x as x approaches positive infinity. Now, since the value at which x approaches 2 is positive infinity, we cannot substitute positive infinity to x. So we have to find out the value at which the function approaches 2 through table of values or graph. Looking at the table of values, we can see that the number becomes bigger as the value of x also becomes bigger. In this case, we can say that the limit of 5 raised to x as x approaches positive infinity is positive infinity. Let's verify the answer using the graph of the given function. We can see that as the value of x increases, the function also increases without bound. On the other hand, we can also say that as the value of x decreases, the value of f of x approaches 0. Mathematically, we can write it as the limit of 5 raised to x as x approaches negative infinity equals 0. Now let's have a base greater than 0 but less than 1. Find the limits of 1/3 raised to x as x approaches positive infinity. With this, we can use table of values in evaluating the limit. Based on the table, we can say that the limit of 1/3 raised to x as x approaches positive infinity is 0. Let's confirm using the graph of the given function. Based on the graph, as x approaches positive infinity, the value of the function gets closer to 0, thus confirming our answer a while ago that the limit of 1/3 raised to x as x approaches positive infinity is 0. Let's have the fourth example wherein the base is a decimal number. Find the limit of 2/10 raised to x as x approaches negative infinity. Just like 1/3, 2/10 is a value that is between 0 and 1. If we substitute some values in x, just like the values on the table, we can notice a trend in the values of f of x. As x approaches negative infinity, the value of f of x becomes bigger. Hence, we can say that the limit of 2/10 raised to x as x approaches negative infinity is positive infinity. Let's confirm using graphs. Looking at the graph, we can clearly see that as x approaches negative infinity, the graph increases without bound. This means that the limit of 2/10 raised to x as x approaches negative infinity is positive infinity. From these examples, we can derive the properties of limits of exponential functions. If b is greater than 1, we can say that the limit of b raised to x as x approaches positive infinity is positive infinity. The limit of b raised to x as x approaches negative infinity is 0. Whereas if b is greater than 0 but less than 1, we will have the limits of b raised to x as x approaches positive infinity is 0. And the limit of b raised to x as x approaches negative infinity is positive infinity.